So this is the first example problem that we are looking at, a simple problem. So what we have in this problem, this is just to get the ball rolling on how you punch in the numbers and how you get the things. So here in this example problem, you have essentially a circular cross section, a solid tube. So it's completely solid, and you're given the radius c equals to 50 mm. Now at this cross section, this may be a part of a beam, and at this cross section, you're having a shear force of 4 kilonewton that you have, right? What it asks you is to calculate the shear stress tau acting over the horizontal diametric line. So let's just go ahead and mark that horizontal diametric line. And so what the problem is essentially asking you is to calculate this thing over here. Right? So say this is passes through the centroid and in neutral axis and all that. In this case, especially in this case, because it's a circular uniform cross section that you have. So what you are asked to calculate that about this line, right? What is the value of tau that you get over here? What is this tau essentially that you get? So that's the question. So this tau is supposed to be found. So you're given all the data and everything, right? Okay. So now that we know that for the tau, let's just write our basic equation that we know that, and now you're also given a hint. This is just to help you out, although you should know to derive these things. Remember that for and we will see where this hint comes into play in this problem. So we know that from our shear formula that tau equals to v q divided by I times t. Right, so we already know this guy over here, that tau equals to vq divided by it. So now let's just plug in the different numbers. So we have in our case that v is 4 kilonewton, so that is 4000 Newton. I'm writing in Newton mm so that in the stress I get in MPa at the end. Let's calculate Q. Q, remember, for Q we either have to consider this area and the center distance from this or this one. It really doesn't matter in this case. Nothing is going to make you help you out even more because it's circular and it's symmetric top at the bottom. But Q, remember, is the area of the chunk which you're looking at. This is the top one, and the distance of the centroid of that chunk from the neutral axis. So the area is going to be, so since the radius is 50, so the area of the entire circle is pi c square. So the area for this is going to be, so I'm just going to consider this part. So for this Q is pi c square divided by 2, because half of the circle I'm considering, times the distance of the centroid for this one. So let's say the centroid lies somewhere over here. So this distance, that is given as 4c by 3 pi from the base. From the base means I'm calculating from here. So from the base, this is 4c by 3 pi. So let's put that forgot to change the color, 4c by 3 pi. We have calculated that. Now I is for that entire cross section. Always remember, I is always for the entire cross section. So I is for the circular cross section is pi c raised to 4 divided by 4 in terms of the radius, right? And lastly, my width, right? That width where I'm calculating, this is this guy over I'm calculating here. So it is this guy. So this is your the overall length that you're talking about. This is t. If I was calculating this at a slightly higher, then your t will be lesser. In this case, t is equals to the diameter, that is 2 times the radius. So t is 2 times c over here, right? So if you take all of these and if you plug this back in this formula over here, what you essentially get is your tau becomes equals to 4000 times pi times 50 square divided by 2, right? Times 4c by 3 pi. So 4 times 50 divided by 3 pi. So if you plug all of these values in and punch in your calculators, you will get tau as equals to this. I have calculated already, 0.68 MPa. So this is your answer. Simple problem, right? Now, if let me ask you something. Now, instead of this being a solid cylinder, what if I gave you this one? What if I gave you this hollow cylinder? So similar, you have a 4 kilonewton load. The radius is 50, but it is hollow now. So it's a hollow beam for that matter, and the inner radius is 20. So it's the same thing. So again, for this one also, if you had to calculate about this horizontal diametric line, which is this guy over here, so your tau in this case is a restricted, of course, to the solid part. The hollow part cannot have a tau. So what is going to change in your, so your formula still stays the same, vq by it. So the only things which are going to change overall is that your q is going to change in this particular case, because now you have to consider just your this area over here, right? Your I is going to change, your T is going to change, and so on. So if you compute that for this one, please try to calculate for this problem. So for this one you will get, and I've calculated this, please work it out on your own. For this one you will get 1.09 MPa. And this number is actually higher than this one over here, because here you see you got 0.68 is 1.09y, and it logically also makes sense because here you have lesser beam material to resist the same amount of shear force, so automatically your stress is going to be higher. So I hope this problem example was good. It was a simple problem example where you were given a section and the force and you were calculating the tau. Next we'll look at a slightly more complicated example of a beam cross section.